Okay, let's get started. I believe we left off with lecture 3, I said. Someone said 3, so I guess I've done 1 and 2 so far. Today we'll do lecture 3 and we'll do lecture 4. So last time I talked, remember I talked about requirements. I remember that part. So today we're going to be talking about analysis and how requirements work with design and how the requirements lead to the design as our topic for today. So what we're looking at is in terms of the transformation. I talked a lot about how to get these requirements with the brainstorming, with talking to the client, observing the clients, all the sort of different requirements analysis in terms of using a domain expert or all sorts of different techniques. So in principle, the requirements should state what the system is going to do, and the design is going to state how it's going to do it. So we have to, once we get the what, I shouldn't say it's the easy part. That's probably the hardest part of the whole system. So once we get the what, and we've achieved that, then the how comes quite easily. A lot of times, a lot of people like to put the how in the requirements document, and that's actually kind of wrong, because then you're limiting the entire requirements of the system in terms of how you want it implemented. Give a year or so down the road, the technique's going to be different, the how is going to change. Requirements never change, though. Requirements will always be the same. So you could take a requirements document from 10 years ago and still say the how today. The programming language is going to be different, platform is going to be different, but the system is the system, whether it's built today or whether it was built 20 years ago. So if you keep that in mind when you start developing your requirements, then you won't make that mistake of putting the how in there, hopefully. So when you're making your requirements in the back of your head, think, well, if I'm going to implement this 20 years from now, I want to make sure it's still implementable. We could still take these requirements and we could still specify how we want it implemented. Which means, requirements such as, the system must work on a Windows platform. The system must work on a Mac. How about, something more generic, like the system must work on a personal computer. That'd probably be more generic. So it kind of gets you sort of thinking in terms of, let's make this last forever. Let's make these requirements implementable. So in practice, requirements and design are sort of inseparable at the same time, however, which kind of just contradicts what I just said. But if you think of the concept, we started with requirements and we built the design from the requirements. They are inseparable. The thing that this slide's not telling you is that we have multiple different design documents. We could come up with different designs for the same set of requirements. So in theory, they are inseparable. They are the same thing. One of them saying what, the other one saying how. And this design document that's created for this set of requirements doesn't work with any other set of requirements. So in theory, they are inseparable, but we can have many different designs of the same system. And as I mentioned before, this is a little bit of review and or new stuff for those people who just started the course. So requirements document is the official statement. It's usually used as a legal document that says, what the system's going to do, what it is we're going to provide. And as I mentioned before, it should have both a definition and a specification requirement. What we're doing is the definition for this particular class. In theory, out in the real world, you'd want a specification as well. Specifications for the developers to do the how from the what. The definition is more for the end user, more for the business world, to know what it is that you actually are building. So it's not a design document. As far as possible, it says what instead of how. Here's an example to kind of wrap up some of the template information I gave you. On page 25 of the course notes is the template I want you to use for your requirements document for your projects. However, this is another example of an IEEE. It's actually kind of an old, and in fact it's simplified. The IEEE standard, the documentation for the requirements doc, it's about 2 inches thick. This is one slide. So, obviously, there's a lot more to the specification than the actual template or the format. And this is just an example. But you'll notice some similarities here. There's always an introduction, there's always an overall description section, and then we have the specific requirements that follow from that. And then any legal copyright stuff might be associated with it as well. And last time we talked about functional, non-functional, user requirements. We talked about all sorts of different categories of requirements. This is a review again in terms of what are the different categories. We can make up our own categories. This is not set in stone. In fact, software engineering is kind of a little different than other engineering disciplines, because in other engineering disciplines, there's a standard. There's one way of doing a measurement. There's one way of documenting something. Software engineering, there's no standard. So how can you have an engineering discipline without any standards? That's why there's a lot of controversy as to, is software engineering really an engineering discipline? Or is it just a, offspring of computer science? So a lot of people don't accept it as an engineering discipline because it's not quite as standard, not quite as professional as some of the other industry-wide engineering stuff. So let's talk about the design document, which is what I want to talk about today. And in order to get to the design document, we have to do some analysis. So in our project, we're not going to write a design document right off the bat. Instead, we're going to do an analysis document, which is a fake, made-up document. It doesn't exist in the real world. But it exists for you guys because we need some way of you pretty much showing what you've done for a couple weeks or 3 weeks or so, which is about how long it should take you to do it. It's kind of the work in progress, and it is actually a rough draft to your design document. So it's the first version of your design document, but we're going to call it an analysis document for the purposes of this course and the deliverable. And so we got the what and the how down, hopefully. So we have stages in the design analysis that occur, and all of this output of these stages turns into the design document. So an example here, we're going to use this university admissions system as a project, because it's really hard to talk about this stuff without, relating it to some example. And so one of the first things you can do, in fact, you can do this in your requirements gathering phase as well. Now look at, who's using the system, what is these systems supposed to be doing? What are some of the features of the system? So we have applicants in this particular example, we have the administration who's using the system, computing staff maybe, academic departments that are using the system, and these are some of the functionalities that they might be using it for. So step one would be to organize the requirements. So gather a list of them, create a requirements document. Step number two is to perform the design analysis. This is where I'm at in the lectures. Hopefully you're working on the requirements document right now in your projects. So you take the requirements, because you can't start analysis until you've done the requirements. Take them and analyze them, and put them in some order to create the analysis and design document and the deliverables that you expect to get out of this. So you have to sort of organize your work in terms of your analysis. And how you're organizing it is you're taking and you're looking at the system from different perspectives. And this is where most people go, what? All right, so this is another difference between engineering disciplines. There's no formal way of doing analysis. But you're doing analysis. And what are you analyzing? Well, here's some example of some design analysis models. And they're modeling the requirements. So here's some common modeling techniques which I want to kind of cover today. So when I talk about analysis, I'm really talking about system models. And if you took the Software Engineering 2 course, we looked at architectural designs. That's one form of a system model. Now you're going to get the basics. So if you were lost on that, because you're taking the course backwards, now you're going to get the basic material. This is what we mean by analysis. So what we have are procedural models, data-centric models, object-oriented models, and this whole category called formal models. In terms of what you're doing for your analysis document, you're doing all of them, actually. And I'm going to give you, and I'll talk about the analysis. Probably won't show you the template till next week, but I'm going to give you like categories where you have to do one of each, and you'll have to put together, and what you're doing is essentially not a formal document. You're going to give me an outline of a bunch of stuff that you're reporting on. Here's my data-centric model. Here's my process model. Here's my UML model or something. And what I'm going to do for the next couple weeks is just go over all of these models so you know what they are, what they're used for. And obviously, you can probably tell there's more than one type of model, and there's more than one reason to use these models. First of all, one of the interesting things about, and I'll call it systems analysis and design, which is what you're pretty much doing, is that there's more than one way to look at the particular system. And the most popular way is to break it out into two separate components, data and processing, which is the traditional standard style of systems analysis and design. So way back in the beginning of software, when the personal computer was invented, blah, 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 or the mainframe was invented, they broke it out with data and processing. modern day, I shouldn't say modern day, futuristic, want to be modern, but it's really futuristic development techniques, puts them back together. And UML and object-oriented design puts them together. Systems analysis and design separates them out. But really they're the same thing. So some of the breeds of models are confusing because people go, well, what are we looking at? If you don't know exactly what you're looking at, the model is useless. It's like looking at vacation pictures and you're going, well, where was this picture taken? I have no idea. Looks like we were having fun, but we don't know what country it was in, or we don't know where the picture's from. It doesn't make any sense. So that's where the labeling, the categorization, and the definition of these models makes a lot of importance in terms of, this is a process model, this is a data model, this is a hierarchical model, this is an architectural model. And I'm going to go through these basic 4 categories. Know that there are more than these 4 categories. This is just a basic overview. In the next lecture, actually, I'm going to go over even more. So this is just a kind of a starting point. And I'm going to take them in order, starting with procedural models. So the procedural model, we're all familiar with those actually. Those are flowcharts. It's hard to get through school without looking at a flowchart at one point or another. Usually it's grade school they show you flowcharts. You know, flow out, you know, and usually actually when you take your first programming course, you know, okay, this was way back years ago when you learned BASIC or something, you flowcharted. Flowcharting doesn't work for object-oriented programming languages, obviously. It doesn't even work for some of the modern stuff like the .NET stuff. Nobody flowcharts anymore. But in the old days, flowcharting was really good as a, you know, predecessor, kind of a pre-step to writing the source code. Now it's actually still used, but it's a pre-step to writing the main software package. So if you don't understand the process or the procedures that are going on in the software, it's hard to model it, it's hard to understand it, it's hard to write the code for it. So hopefully every one of these types of models, and you use a combination of these different models so that you can get a better understanding of the big picture, hopefully. So, alright, so we have symbols, and don't worry about all the symbols, and you're not going to be graded, you're not going to be tested on the symbol sets for any one of these models, so don't worry about that. But we have some basic symbols that are used, and all of these things are not very complicated. A lot of people use like Visio for this, but you know, it's overkill. A lot of these models are written in PowerPoint, actually. So here's a flowchart example of the University Admission System, where we have a form that is received, and then we have a, you know, true or false, yes or no. I don't even know what this is doing. You know, I could probably figure it out, but anyway. You know, is it update the database? You know, if it's complete, go here to evaluate. You know, if not, you know, if it fails, notify the student. You know, your application is not complete. You know, or take another route. It's a common flow chart in terms of the processing of the data, and also the processing. And this is the interesting part. Just because it's not showing the data doesn't necessarily mean it's not processing the data or showing the processing of the data. And it is, actually. And then from this procedural model, we have other people who say, well, I don't like the flow chart. And this is another thing they had you do when you were writing Visual Basic, or, actually, this is QBasic. This is prior to Visual's anything. It says, oh, let's write some pseudocode. Also, a lot of instructors actually taught programming by having students write pseudocode, which is kind of ridiculous if you think about it. But pseudocode is a language in itself, because it's really good for procedural modeling. So believe it or not, this is another form of a procedural model. If you don't like pictures, you can write the pseudocode. This is hard for people to understand, though. That's easy. You know, you look at that and you can understand what the processing is going on, what type of processing is going on in this program. Here, you gotta be, you know, your average business person would jump 10 feet away from this and go, oh, I'm not gonna look at this. This is programming. They don't even know it's pseudocode. It's not even programming. But this is for an audience of, let's say, a programmer who might be interested in looking at this. So another point that I should mention is that these models have different audiences. They're made for different groups of people. So you could do several different types of procedural models, and this is just 2 types I'm showing you, that could apply towards many different groups. So you build the right model for the right group, you show the right model to the right group, hopefully, and it increases everybody's understandings, hopefully. Alright, so if we're not doing procedural, we could do, and this is the interesting thing, is this data flow model, which is now, this is talking about processing. Data flow is talking about data manipulation, data changes. And the data itself sometimes falls into a procedural model category. If you're talking about UML, it is. It's all together. So there's a little bit of overlap between what category you would put something in. I would actually put data flow in more of a data model category versus a procedural model. I wouldn't call it a procedure. However, if you take a look at what it's doing, it is kind of a procedural, if you think about it. It's looking at the processing. So these are the symbols used in your average data flow diagram. This is the data flow diagram with the symbols put together. Again, don't worry about the symbols. But we have the same program. It's the same identical university admissions system. Here, instead of the application form is being received, we have a process bubble. There's my mouse. Process bubble here that's receiving the application. And then the completed application is sent to an evaluating process. Okay, we have all the pieces we needed, all the transcripts and everything. Now we're going to evaluate it, we're going to reject it, or we're going to give them an offer. Yeah, you can come to school, no you can't. And then we have these things I probably should mention are called terminating symbols. Terminating symbols connect diagrams. So you could take this little thing as a spoke and connect it to another diagram. And say, well, if we reject it, what happens? Out here, another diagram will say, oh, we sent a letter to the student. We blocked their caller ID, so we can't accept their calls anymore. I don't know how harsh we're going to be. We notified a local paper and we put an ad in there that says, this student's, not qualified. All these things that we could do to reject this particular student, or offer. We send them two tickets to a Sharks game, and we, treat them well. Hopefully, I don't know. None of the schools ever do that anyway. So, all right, but that's how we can connect the actions together. And here's an example for which we have, you might notice here, we got it open, open, open buttons, open, 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 and then we got a solid. Sometimes people do that to say, we do have a continuation. We don't have anything. This means we do have another diagram that maps up with this. It's solid. It means that there's a connection point on there. This is just going out, the empty circle is just going out into oblivion. It's just like, whatever. We're not going to specify what we're going to do. But here we have another diagram. You can see this is another diagram of, this one here says university admissions. This one here says the assemble the application stage. So we have multiple diagrams showing different components of the system in terms of its data flow. And some of them connect together, some of them don't. And some of the diagrams are showing different levels of abstraction or different parts of the system. So we create many different, even though we could probably create one of each category, we end up creating more than one of each category because we need to show things. Basically, the concept is you don't put too much on one diagram. If you put too much on one diagram, it's hard to actually fit it all on a page, believe it or not, and it looks too complicated. So it makes it easier if you split it out and just connect the diagrams together, which is actually referred to as functional decomposition by terminology. We're taking the functions of the system, we're decomposing it, and then we could put labels on it. And for example, here we're calling this the assembly application stage. Or we could call, a different part of the system something else. It actually bleeds into our modularization. It actually allows us to create different modules at the same time. So as we're thinking about the diagrams and we're creating different levels of diagrams with different focuses, it's helping us analyze the system. It's helping us break it down. A byproduct to all this is now we have our module decomposition. Eventually, this is going to lead into, hopefully, a better understanding of how should we break the system out. And sometimes when we do this, we go, well, maybe this assembly application stage should really be two separate stages and not one. And then we can decide, well, maybe we could put evaluate, initial evaluation and receive. We could probably break that out into two separate modules or something. So in a lot of cases, you'll see the diagrams have a different set of abstractions than the functional decomposition of the system. When you see that, oh, they learned something. When they were breaking out the models, when they were breaking out the system in terms of the modeling, Now they have a better understanding of the system, so now they have different modules that were created out of that led to that. Sometimes you go back and you redo the diagrams. Sometimes you don't. You just leave them. If you leave them, then you can see the reasoning. Then you can see the logic, because if you didn't reach the right conclusion, it's better to go back and see what you started with. And there's people that go back and change everything. They go back and let's just reverse everything, put it all back, and then you're fixing it. So you've undone your analysis essentially, and you're now giving your conclusion without even showing your analysis. So part of the analysis stage is to make mistakes, is to actually show the mistakes, to come up with different diagrams, different levels of abstraction, different pieces. It's a troubleshooting, brainstorming / an investigation type of activity. And there's actual value to saving that, archiving that, and not going back and deleting everything that was wrong. It's kind of like when you write a research paper, as an example, and you don't use track changes, you just keep changing it and changing it. You get a really good version of it, let's say, and you're happy with it, and all of a sudden you go off on a tangent, and you destroy the whole thing, and you can't go back. It's gone. Like, sometimes you wish, I could just go back to that when I liked it before I actually did all these other changes to it. So sometimes, keeping the history is good. That's why people will save things, hopefully. Save it and use it. And you could also have different sets. You could have different archives of different sets of diagrams that show different things. And sort of like writing a research paper, so you can go back in time and revisit something. Here's another one. This is the completed application stage, where we have this box here at the bottom, that's just a little different. And for those of you who've taken my database class, you're already extremely familiar with entity relationship diagramming. And this box down here is an entity. So the symbols being used, we have entities down here too. For those of you who didn't have the database class, you're probably wondering what an entity is, and it's the same thing as an object. So, and if you haven't had object-oriented anything, you don't know what an object is, you don't know what an entity is. Just think it's a person, place, or thing, or concept. Represents some component of the system that can be identified as a thing. It's the same thing as a thing. So we have entities in here as well, but this is really a data flow diagram, not an entity relationship, because the focus of the diagram is supposed to be showing the processing. If you make it too much of a hybrid, it gets kind of difficult in terms of, well, what kind of diagram is this? And you can't figure it out. If you can't figure out what kind of diagram it is, then I'd say you have to go back to, step number 1, figure out what it is you're trying to show. Because what it is you're showing, what you're reading from the diagram, is not going to be what it is you intended. And if you don't even know what you intended to show, then it's garbage in, garbage out. Essentially, you're not really actually helping anything. You're making things worse. You're adding more confusion to the already existing confusion. So requirements analysis versus the system design. So requirements should hopefully make some minimal assumptions about the system design. As an example, you don't want to say this is going to be an object-oriented program in your requirements document, because what if you make this 20 years from now, there's no such thing as object orientation anymore. Which there may not be. Who knows what's going to happen with object orientation. You're limiting yourself as well. You're saying, oh, well, what if there's a better way of doing it? And I've said in my requirements it must be done in an object-oriented fashion. Now I've just restricted the entire system design to something that's maybe even impossible to create. So the requirements definition must be consistent with computing technology and resources that are available. Which is kind of, again, going back to, well, all right, so you're telling me I can't put object-oriented design in there, but I have to use something that's available. I have to be, the key word here is consistent. It must be something that is implementable. Because, I think, well, if I had a wish list, this is like what you do to kids. You say, give me your wish list for Christmas. They're going to have everything. I want a car, I want a house, I want a boat, I want a plane, submarine. Some of that stuff's going to be impossible to get them. However, they're going to ask for it. So people do this in a requirements document, and they end up being inconsistent with themselves. They say, I must use a database. And it comes back to them, must not use a database. Which one is it? Or it's an infrared product, and it must connect with computers that are 20 miles away. It's like, no, that's not going to work either. So sometimes people, they say technology, oh, it has to be Bluetooth. Yeah, but it's in, the implementation that you'd have to create for this is completely impossible to create. If you do that, what happens is you make the requirements a bunch of junk, essentially, because now you're thinking, well, I'm not supposed to be thinking about the how. I'm only supposed to be thinking about the what. That's why I go back and say, make it as vague as possible. You must use some sort of a wireless technology. So then we can pick among infrared, Bluetooth, wireless, connectivity, anything that might be available in terms of current technology. And then consistent, meaning if you're talking about a wireless technology, then make it consistent with a wireless technology capability for the modern times. And then in the future, if the wireless technology changes, now we have global wireless communications. We have cellular service that's available for laptop computers at the same price as wireless, free. Let's just call it free. Then, you at that point you come up with a different requirement stock because times have changed too much. In fact, just because you can implement it doesn't necessarily mean you want to implement it in the future as well. So in practice, analysis, and design are interwoven, going back to that kind of statement as I made before. They are, in a lot of ways, and I think you can kind of sort of see how they might be interwoven. Okay, so now we have this thing called scenario planning. It is a form of modeling. More modern. In fact, this is more UML object-oriented. You guys are familiar with object orientation? Show of hands. This is brand new to me, object orientation. Nobody? Because nobody is going to raise their hand. And this guy in the back, yeah, it's new. Thank you for being honest. All right, so let me discuss object orientation briefly, because we do have some people, and there's probably people listening to this video who don't know anything about object orientation. And it merits, especially with the Software Engineering 1 course, it merits a little bit of discussion. And it's nothing new. It's nothing new. It's everything that we've done for millions and millions of years. Actually, not really millions. I don't know how long. How long has software engineering been around? Maybe late 80s, perhaps? Okay, early 80s, late 70s, early 80s. And if I had to put a time frame on when software engineering actually became a field. Object orientation is absolutely nothing new. The only thing different is the terminology and the people that think it's better than sliced bread. That, it's like, it's the same. We have sliced bread. They're just putting a different name on it, is what they're doing. Okay, so how is it different? Well, we have systems analysis and design, as I mentioned before, which is the traditional way of describing the development process in terms of a methodology. And yes, we're talking about methodologies again. So we have software development life cycles that are methodologies that go along with the development process. I talked about that in week 1, where we had the waterfall, spiral, evolutionary, rapid application prototyping. Those are software development lifecycle models. Now we also have development models or implementation models. 2 of them that are very common these days, and there's more than just 2. Systems analysis and design and object orientation. We have, believe it or not, like a whole, millions of other ones. However, it's not as popular. The 2 that are very popular, in fact, the one that's the most popular right now would be object orientation. Those 2 models are very similar, however. So let's talk about systems analysis and design first. I mentioned already it takes data and processing and separates them out, puts them into 2 separate buckets. It says models the system in terms of its processing, and it models it in terms of its data and what it's the inputs, the outputs, and the processing of the data, which goes along with the traditional information systems models. Input, processing, output, in terms of what computer applications are doing and programs are doing. In fact, we still see careers. You could be a systems analyst, you could be a database architect, you can be a systems designer, systems programmer, systems anything, analysis, anything is systems analysis and design from a traditional point of view, although the job titles are often misused. can have a systems analyst who's working with object orientation. It would really be an object-oriented analysis, analyzer, or analysis, or domain analysis. But anyway, so there's a little confusion, especially in the marketplace, with job titles, but most of them are still using the traditional titles of systems analysis and design. So it's really limited. If you think this was developed back in the late 70s, early 80s, you know how long ago that was? You know how many programming languages passed that was? This was before Visual Studio, before Java, before any of the modern day programming languages. Very old, and it was very basic. And it followed, when software engineering was becoming an engineering field, it followed in other engineering sciences. So we had process models, data models, architectural models. All of those are systems, they're all like, old-fashioned traditional labeling models. And they were showing very basic components of the system. So along came object orientation as a programming methodology. And the interesting thing is nobody actually takes an object-oriented design course. They always take an object-oriented programming course. And there's a difference between design and programming. There's object-oriented analysis, and then there's object-oriented design. So we're looking at analysis and design, kind of like systems analysis and design. It's actually the same type of methodology. But everyone skips the analysis, and they just do the design or the programming component of it. And they forget, well, there's actually a methodology for the design. And in a nutshell, what object-oriented analysis and design does that's different is it takes the data and the processing, adds them together, changes the label of the entity to the object, and then adds millions of other modern-day diagrams and diagramming techniques that never existed in the past, that are supposed to be showing a different component, and all of the diagrams overlap. So we have this methodology called object-oriented analysis and design. So we had to come up with, or they had to come up with, some sort of terminology for the modeling. And it was called UML, or Unified Modeling Language. It was a way of bringing all the models together at one point. UML is not standard. Object orientation is not standard, actually. In fact, among different programming languages, you have different implementations of object orientation. Some of them are truly object-oriented, some of them are hybrid. They're sort of object. Example, Java is a truly object-oriented programming language. C++ is a hybrid. It doesn't follow the same rules. It follows 90% of them, but not 100%. So it's not really a pure object-oriented language. Smalltalk is a pure object-oriented language. Object-C, pure object orientation. So we have some languages that do follow. We have some languages that don't. We have a lot of inconsistency in the terminology as well. So what modern-day software engineers do is they try to not focus on the design methodology in the analysis stage, but rather focus on understanding the system, figuring out, how are we going to see it from different levels of abstraction? What different levels of abstraction do we want to see this with? And the interesting thing is once you create the systems analysis and design models, it takes you about 10 minutes. You can transform them into UML models. Because the models, believe it or not, are practically identical. The only difference, and now for the people that no, they're not identical. The only difference, they're not identical, I said practically identical. The only difference is that we have a huge subset of other models. As an example, the entity, we haven't talked about it yet, but the entity relationship diagram that we use, if you're in the database class, you're familiar with that already. We use it to model the data of the system. That translates into both the object and the class model of an object, of a UML world. It translates directly because the entity is the object in the object-oriented world. But we don't have inheritance in systems analysis and design, but we have inheritance in UML. So now we have inheritance diagrams to show the inheritance. And we have sequence diagrams to show the sequences. And we have a bunch of other, and one of the use case scenarios and scenario planning. But scenario planning and use case scenarios came out of systems analysis and design. it was copied directly over into UML. It's not a unique concept. We've had test cases, test scenarios, scenario planning, ever since the 1980s or whatever, right from the beginning, long before UML came around. So as we go through some of the different diagrams, and I know that was a really quick introduction to object orientation, and this is not a replacement for an object orientation course, obviously, but I'm trying to put it into perspective in terms of how it compares with the older methods that I'm talking about. And when I say older, it doesn't necessarily mean outdated. It just means in the sequence of history, they appeared first. So object orientation is just another, let's call it a redo, makeover. Let's call it a makeover. They splashed some paint on it and washed the windows and added a few dangling things from the rearview mirror. And all of a sudden, it's a brand new car. It's really the old car, old engine, old car. It just has a new paint job, some cleaned windows or something. All right, so going back to scenario planning, which a lot of people, when they think of scenario planning, they always think of UML, which is why when I looked at this slide, I went, oh, scenario planning. Oh, I better talk about UML first. It's actually systems analysis and design. We have an equivalence that's identical in UML. So now you're learning UML and you're also learning systems analysis and design right now. One of the classic ways, in fact, scenario planning can be used in requirements gathering. It can be used in analysis. It can be used in design. It can also be used in acceptance testing. Because what we have is a checklist. Scenarios are just different ways people are using the system. And it's a checklist on the features. So it helps us not only right from the beginning, but all the way through the development lifecycle model, analyze and understand the system. So what we're doing is we're creating scenarios that are describing how the system is going to be used in practice. So we can write them out, we can draw stick figures, or we could put them in a big old template, like in a matrix or something, and we can actually keep track of these scenarios and how they're implemented. And we can use these scenarios to write our requirement stock. So a lot of people start out doing scenario planning, before they even create the requirements document, because you go, number one, I'm building an air temperature controller. Number one, must be able to raise the temperature. It's a scenario. Must be able to lower the temperature. Must be able to turn the system off. Must be able to see what temperature it is right now. All the different things that this user might. Those are scenarios. So scenario planning is you're planning out a list of features. When we talk about scenario planning, we're usually referring to the analysis stage or the requirements stage. When we talk about use case scenarios, then we're in design. Because scenario planning turns into use case scenarios, which turns into use case testing, which turns into acceptance testing. So if we use it as a methodology right from the beginning, we have it and it's available to us throughout the cycle. We don't have to reinvent the wheel. So I haven't talked about testing yet, but theoretically, we can start with our testing right when we start with our requirements. And this is how we're starting. We're coming up with scenario planning. All right, so scenarios are helpful in terms of the requirements elicitation as people can relate to them readily. They're abstract statements about what the system is required to do. And they're useful for adding detail to an outline of your requirements descriptions. So you can actually kind of create your own scenario planning. And actually write at your requirements. In fact, the interesting thing about this entire project that you're doing, the more work you do now, the less you have to do later. Because you're taking all the work that you're doing and you're reusing it, unless you're throwing it away. You have it. So all the work you put into your analysis turns into your design. All the work that you're doing in your requirements turns into your analysis, essentially. And going back to the concept of modeling, which is my theme for today, this is a model that's using scenario planning. And it's a scenario example of an ATM system. And it's just basically looks like a flowchart, but it isn't. Let's go back. It probably is a flowchart. But it's actually kind of combining, and if you think about it, it's actually kind of combining processing with data loosely, but it's not formally doing it. It's not actually showing you data versus processing. It's kind of looking at scenarios. So going back to what I said about systems analysis and design, 90% of the models separate the two out. Small percentage, maybe 10% of the models, and this would be an example here, put them together. Because think about it, we have a PIN, we have a card number, those are pieces of data that are being checked. So how are you gonna separate that out and only show the processing? So you can have something here, you know, that's going to say validate the user. It's processing, but it's using data to validate the user. So it is kind of putting things together. So scenario planning is usually shown in boxes. This is what it looks like if you're doing systems analysis and design. I'll show you further down when we start looking at object orientation. It's little stick figures and arrows going to bubbles. And those are more, there's still scenario planning, but they usually call them use case scenarios. So I actually talked already through this slide, but let me give you the formal so you can read it for yourself. The formal information. I just covered this slide first. So in terms of use cases, that word is used a lot, actually. So put together some use cases. In fact, business people use use cases a lot. Well, modern day business people use the word. Oh, the word is constantly being used. Nothing more than scenario based on a. And here we go. Now it's formally said here it's based on UML, Unified Modeling Language. It didn't. It's based on it. Current modern day people go, oh yeah, that's object orientation. Because now they're just learning it, even though it's been around for years. Think of the concept. Did we not come up with usages back when we were developing how an elevator should work? Or how something, you know, some small little thing like a car. Yeah, what kind of uses? Well, you have to put in reverse, drive, you know, different uses. So in terms of use cases, it's normally a set of uses, set of scenarios, and describes all the possible interactions of the system. And this is where object orientation takes over. If we have the use cases, we can have sequence diagrams that can be used to add detail to the use cases. The sequence diagram is going to tell you from this use, we go to that use, we go to that use. We didn't have sequence diagrams in systems analysis and design days. You could have a process diagram that did it, but we never used to have sequence diagrams because usually the stuff didn't communicate. We didn't think that the objects actually communicated back and forth. So going back between object-oriented analysis and systems analysis, the entity turned into the object, but the object has identity, state, and behavior associated with it that the entity never had. So the object is an evolution. It's a modern day 2011 version of an entity. And it changed, it grew, it morphed. Now the object can take on multiple identities. Objects can, you know, have polymorphism associated with them. They can do all sorts of things. They can be inherited from other objects. They have all sorts of different properties associated with it, and they can send messages back and forth, and they can communicate now. They've learned how to speak between different objects. Objects that were entities in the old days is kind of like how man evolved, the caveman versus the modern day person. We didn't have computers back in the caveman days. You know, we didn't have microwave ovens. So now the modern day person uses a microwave, has a computer, cell phones, you know, anything modern. So that's pretty much happened with the object. It totally transformed into the modern day object, which is a lot more powerful. So that's why people like object orientation. They think you could do a lot more with it, and you actually can, because think about it, it's more evolved, it's enhanced. So here's our use cases with UML. It's kind of the same as that. But you can probably tell by looking at the diagram, that's very old-fashioned looking. Yeah, it looks kind of old, structured. This is kind of fun. We got stick figures, we got bubbles, we got arrows and stuff. It's the same thing. It's really showing the same thing. We got library, users, lending services, or user administration. And the reason why we can do this is because now these objects, an example, this would be a library object, this would be a supplier object, is more evolved, does more. We can incorporate more behavior, more states, more information in that object. So we don't have to diagram it out as much because it's doing a lot more than the old object than the old entity used to do. You don't have to know any of this stuff at this point. Just giving you examples of how the use cases are applied. Here's another way of doing it. So we have the use cases if we add the sequences in. This is a sequence diagram. So UML added in the concept of one use case leading to another use case leading to another use case. You put the card in, you put your PIN in, it's going to send you to the main menu. Main menu, you press deposit, it's going to send you to another menu, which is a sequence of events that occurs. This is how you'd actually diagram it out if you were using a UML approach to it. So we have the use cases that are combined into it, and then, but most people would call that a sequence diagram versus a UML use case diagram. It's really both. As we have the supplier, and we have these little boxes to show different sequences of. We could break it out into about 1, 2, 3, about 4 or 5 different diagrams probably. When we put it all together in one, it looks clearer, looks easier to understand. So in some cases in UML, you could pick out a diagram that makes the system look easier to understand. Makes it a lot more flexible. You have more choices as well, which is why a lot of people like object orientation. So what's after requirements, as I've talked about so far? System development stage. So the next project deliverables. And just to clarify the point, you do have an analysis document and you have a design document. The analysis document is going to have all your system models, your diagrams, and your flowcharts in it. Your design is going to contain the blueprint of the system that's going to be implemented. So as we know, if we're going to outsource this, we take the design document, we ship it out. If we're building a house, we take the design document, we contract out we get quotes from like maybe 3 contractor companies maybe. We say, which one's the best? Which one can do it faster for the least amount of money? Or maybe the highest quality. Maybe they have good work ethics or something. We judge the company and then we hire somebody to do it. Which is kind of like the modern flow development these days. Because even if, let's say for example, even if you're not going to outsource it, at this point after you have the design document, you can hire a programmer. Why have the programmer on staff for the last 6 months? You don't normally have them on staff for 6 months because they're not programmers are not part of this process. Programmers take the design document, which is the blueprint, and they make it happen. They implement it. They write the source code for it. So in software engineering, it differs from other engineering sciences because you could be a specialist in a lot of different areas. You could be a database architect. You can be a business analyst. You can be a requirements analysis, a domain expert. You could be a programmer. You could be a system integrator. You could be a tester. Work in QA. You can do all sorts of different jobs. Yeah. All right, I'm also going to cover lecture 4. It's actually pretty small. It's 24 slides. It's pretty small. And well, lecture 3 and 4 sort of go together in terms of the system modeling. So. Alright, so lecture 4. Actually, this slide set was originally designed for a Monday, Wednesday, Friday sequence of like 45 minutes to an hour. So I have to cover 2 lectures in order to do a Tuesday or a Thursday or a Wednesday, one day a week type of class. I have to cover more than one. They just don't work out that way. I could rewrite the whole thing, but why? Anyway, so system modeling, the analysis stage, what we were talking about before. System model, the abstract definition or description of the system, whose requirements is going to be analyzed. Interesting. You don't put stuff in the system model that's not in the requirements documents. I've seen that a lot, actually. You have a requirements document, and then you look at the system models going, oh, where's there a refund system in this? Not in the requirements. So technically what you're supposed to be doing is taking the requirements and writing the system models. And here's the interesting thing is what you can do is have a different group of people do the requirements. And then they're done, they can move on to the next project and then they do requirements. And then all they do is requirements. And you have a different group of people that might be doing the analysis. Then you find the inconsistencies. After you've learned about the system, then you go, oh, well, there's no refund module. Or there's no way of printing out the reports. Or there's no feature in here to do this or that. And then you realize how good the requirements people are versus, what they've left out. So here's some general objectives of the modeling in terms of, now you're the analysis team. Somebody else gave you some requirements. Now you're taking these requirements and you're looking at them. And the first thing you have to do is kind of define what kind of perspective are you looking at. And not really who's your audience is what you're trying to learn, essentially. So the modeling helps the analysis analyst, I always say that word wrong, the analyst is the person who's doing, so a systems analyst, so what's a systems analyst job? Traditionally, they're supposed to be analyzing requirements and system definitions. They're supposed to be building the system design, the systems analysts. They're not normally writing requirements. They're not normally source code. They're not writing source code either. They're in between. They're analyzing the system. So you could bring a systems analyst in, as an example, to build an upgrade. They're not doing any of the coding. They're doing it, but what they're doing is analyzing the requirements, perhaps. They could be working with requirements, analyzing requirements of the new upgrade, and then presenting the information in terms of these different views, perhaps, and writing up the system models and things. And they're doing the analysis work. They could also be doing the requirements generation, but normally somebody else knows what they want. You hire a systems analyst because you have this old system and it's now the year 2000 and you need it to be compatible with the new dates. You already know what you're hiring this person for. So the person comes in and says, well, we can't do that. We got to build you a new system. Or no, we could do that. It's going to take about 5 hours. We could probably change all the dates in here. We still have the source code for it. We could do it. We could recompile it. So the systems analyst's job is very different than other types of jobs because you don't really know what you're going to be doing in a lot of different cases, especially if you're working for a consulting kind of company. You might be on totally different types of projects all the time. Because there's no such thing as a systems analyst like there is like a programmer. When you're doing Java programming, you're writing source code in Java. When you're doing systems analysis, who knows what you're doing? It's a little bit more broad. So people like to use that word analyst in job ads because it's so generic. It's like engineer. We're looking for a computer engineer. Okay. It's like, what do you want me to do? And then you pretty much have to ask what you want me to do. All right, so there's different models that are presented from different perspectives, and here's just an example, and these are just 3 of the common approaches. External, functional, and structural perspectives. So the external is the context of the environment, showing the system in terms of how it's working and the environment that it's supposed to be running in. The functional is looking at the functions of the system. It's modeling the requirements, the functional requirements, essentially. And the structure showing the data architecture, the structure in terms of the database architect, or database architecture.
What are the participants in this?
Oh, go back, yeah.
What are the participants here? Business analysts, can you collect the requirements here?
Business analysts don't normally work with writing the requirements, but they can work with the requirement solicitation, planning. Yeah. Because you need a business analyst, especially if you're doing process redesign or business process redesigning, BPR stuff, where you're doing continuous process improvement, QA stuff. You're doing security related stuff. You bring a business analyst in to say the HR people should not have access to the such and such feature, or they're analyzing the business rules and they're the business experts, and they're not necessarily technical people. You may not know anything about software.
My question is,
who
are the participants in the system design?
In the system design, you have a wide variety. You could bring in a database architect who is just going to work on the database. You could bring in an object-oriented person, designer, analysis designer, who's just going to present the system in terms of object orientation and show you how the model might apply towards the system development. You could have a systems architect who's going to do all of the systems analysis and design work if you're not taking an object-oriented approach. Sometimes you bring in both because you could choose. You have a systems architect. In fact, there used to be a piece of software, shareware program called Systems Architect, and all it did was essentially like Visio. It allowed you to do, a free version of it used to be shareware. Data flows, entity relationships, process diagrams, data diagrams and stuff. And they're just basically analyzing the system and creating models, is what these analysts, I can never say that word. This is what the analysts are doing. They're modeling the system and reporting back. They're not necessarily designing the system, but if you think about it, all of their work goes into the design. Once you understand the system, then you can build a design for it. And hopefully you have design options, so you could pick from a couple of different alternatives that you might be able to select from. And if you don't know you have choices, then you're stuck with whatever somebody dreamed up And then you figure out, if you don't hire any of these people, you have the programmer do your analysis and your design and the implementation, which happens a lot, actually. And then you're relying upon the programmer's previous experiences and all the other jobs that he or she has done. And you're essentially going, well, you've written a financial accounting program before, right? And the guy's going, yeah, maybe. Yeah, I wrote one for this other company. Okay, so you have experience in it? Yeah. Okay, so write us a program. Here's the requirements. And they're going to probably base it off of something that they did in the previous job. You know, they're going, oh, we had accounts payable module, we had accounts receivable module, we had this and we had this. And they're going to be mimicking that. But how do you know that was the best way of doing it? So that's why you hire the systems analysts to come in. They analyze the requirements, they model it, and they go, well, you could do it this way, or you could do it that way, or you could do it that way. So you have a bigger picture. It's kind of like the more informed consumer will save money and buy something that's going to last longer. It's like why people shop for cars. They look at the features, they look at, you know, warranties, service records, Blue Book, you know. Give me the Carfax, you know. They get all the information. That's what a systems analyst is really doing, is getting the information and modeling, so that the people who are making the decisions in terms of the design are making an informed decision. So it depends on the type of analysis that you need to have performed as to what type of person you're going to bring in. So every team's going to vary a little bit. These are usually temporary people. They're not working, unless you're working for a consulting company that's doing development project after development project after continuously. You're probably going to be contracted. A lot of consultants do this, actually. Actually, a lot of business analysts they always work as consultants. So, more flexibility. How often do you have to fix a company? Hopefully not. If you fix them, hopefully they're not going to be broken again. Like the Maytag repairman or something. All right, so model weaknesses. It's hard to model non-functional requirements. You think about it, how are you going to model color? Encryption, not encryption, that would be functional, but let's say whether the password field is shown to the customer or not. They don't always include information about whether the models are appropriate for the given problem either. So just because you said, let's use an object-oriented, I heard that the object has evolved. We're going to use an object-oriented programming methodology for the software implementation. How do you really know that you actually have chosen the best model? Maybe the system, because object orientation is not the best thing in the world. It works for certain situations, but it doesn't work quite well in other situations. Small example, embedded systems. Small devices, Unix, Linux development work, drivers, hardware, heavy hardware functionality. If you want a direct relationship to the hardware, you're going to use a lower level language. You're not going to use them. You know, why use? Well, object orientation is good for huge system development, distributed system development, multi-platform development. You know, so there's a case in which one methodology makes more sense than the other. The modeling is not going to tell you that. It's not going to tell you that, you know, the model looks great, but you might be going around the wrong path. So that's why people use a variety of different models, because you just don't want to show it in one. So even though you're doing object-oriented design, perhaps, you're still going to be looking at systems analysis and design, traditional models. You're still going to be putting together a data flow diagram, or an entity relationship, or a process-centric or a data-centric type of model, because you have to in order to really understand it. And might also produce too much documentation. In fact, you'll probably get this when you start looking at your analysis document. You'll be like, what is all this crap in this document? And if you go out and you search on the internet for analysis and design documents, or just look at design. Just do a Google search, put in design document, and you can pull up. Usually they've archived them somewhere, and usually they're password protected, but sometimes you'll find some company who has it available. And if you find when you look at it, you'll notice it's like 200 pages long, 300 pages long. You're not creating that for this course. Actually, that's a real one. Think about the concept. It takes 2 years to build this software. They've worked on this document for 6 months to a year or so. Half the work goes into it before the programming even starts. Programming is the fastest part of the entire process. It takes you twice as long to fix the bugs after you've programmed it. So it's just a small component of the development. So these documents can be really big and they can be hard to read. And what ends up happening is nobody will read them. They'll look at that and go, oh man, I don't have an entire weekend to dedicate to this, so I only have 5 minutes. They're not going to read it. And the models might sometimes be too detailed and difficult for users to understand. You show this to the user, and the user is looking at this going, what in the world is this 200 pages of garbage that you just gave me? I don't understand any of it. So here's our systems analysis. So the methods for data and modeling, to reiterate the point, we're looking normally, and I've mentioned this already, but here's your formal slide. These are the components. It usually consists of entity relationship diagrams. And these diagrams are created whether you have a database or not. They're not database oriented. I use this because it's used very common. It's like 90% of all developers will use an entity relationship model to model database requirements, database design. However, it's also used for system design as well. It's the same model. So if you've learned it already, you're halfway there. Data flow diagrams, we saw a little example of that with that university registration system. Data dictionaries, process descriptions, data dictionaries. Important for the design. How do you know what the such and such module is? How do you know what the such and such component is? Because what you don't want is people calling the wrong component by the wrong name or using it incorrectly. And or if you don't have a data dictionary, what do you end up with? It's kind of like the English language. 10 words that mean the same thing. Which one are you going to use? Depends on which one you learned, I guess. So there's many different ways of saying something, and that adds confusion to the project. Adds confusion to development. And then object models. So object models are sort of used in systems analysis, whether you're doing an object-oriented design or not, because they add some things that the regular structure approach never had. Many of the models are blurred distinctions between analysis and design, because the analysis leads to the design. And the modeling types, these are more modeling types. So I gave you before different ones for process modeling, data modeling, system modeling. So data processing is essentially the same type of model. It's a data-centric model, showing the data and the processing. We have the composition model. This is a new one listed. And if you're starting to get the impression that there's a lot of models, there's hundreds of these models. And it depends on who you're working with as to what they're going to call it. I mean, nobody ever uses composition model anymore. They use contextual model or context models, showing how the entities are composed with other entities in terms of the context of the system. But it's really a composition model traditionally. Architectural models, principal subsystems of the system, classification models, common characteristics. Is this classified as input, output, classified as the processing. Response models, showing the system's reaction to events. If I was building a network intruder detection program, I'd want a response model. Am I going to build a response model for an accounting program? Probably not. But I might build an architectural model, or I might build another model. So we have many different modeling types, and it's really domain specific as to what you're going to choose. Air temperature controller, I do a response model. How fast does it take? What happens when I press the up arrow in the heat? Does it actually get warmer? Does the heater turn on? Stuff like that. So the rest of the slide, I'm going to kind of go through it not quickly, but I've already talked about most of this stuff already. That's why I said the set's pretty easy. It's going through all of these different types of models with different names. So to confuse you even further, context models, that's the more popular way of saying composition, or sometimes they overlap with architectural models. So the context models are used to illustrate the boundaries of the system. So then it sounds like an architectural model to me, showing the context. Concerns with the decisions of where to position the system boundaries might be important if you're building a network application. Let's say a shopping cart. And then you need to know the system boundaries with other systems, other credit card processing. Architectural models show the system and its relationship with other systems. So if you call it an architectural model, you're looking at systems and subsystems. If you called it a context model, you're more generic. You're looking at, the boundaries of the particular system. So sometimes the trick is getting the right terminology in terms of the label on this particular model. Here's the context of the ATM system. We have different subsystems that are apart in terms of boundaries. We have an account database, let's say, that may not be associated at all with the auto teller system. And then, the security system may not necessarily be associated at all with any of these other things either. They're just different systems working together in terms of boundaries between, this would be considered the security component, this would be the accounting system, this would be some of the other components. The process models we've seen already, it's the data flow. It's processing the data. So data flow models can be used to show the processing and the flow of information from one process to another. So the overall processing, and here's our data flow. This is actually a good example of a data flow diagram, more realistic than that last one we saw. And you see this box around here showing you context, sub-data parts. So this is a different system than the rest of it, the ins and the outs from the system. So we can combine actually, the concept and say, well, this is in the context of the such and such processing. I'm going to draw a little box in here, and this is how this processing works with that processing, So can you get kind of creative? And systems analysts are really good at modeling. You got to be good at drawing pictures. If you're not, you're going to be a bad systems analyst. Data flow diagrams are used to model essentially system data processing, as we've seen already. Processes the steps of the data flow. So shows an end-to-end processing of the data. This is why we have those, not in here, but we have those process termination bubbles, termination points. So in terms of it, the functional perspective is what we're looking at when we look at data flow, because we're looking at the functionality of the processing. How are the applications rejected or accepted? That would be the data processing of whatever formula we used, kind of like a credit check. How do you get a number that's associated with your creditworthiness in this country? There's a process. And there's 3 different credit reporting companies that do different processes. So depending upon which process you like the best, you can have a higher or lower score, depending upon what you check. So tracking and documenting how the data is associated with the process itself and the overall understanding of the system. So it's used to show the exchange as well of the data from one system to another in here. This is pretty much showing more of an exchange as well. Data dictionaries. Haven't talked about these yet, but sometimes referred to as repositories. They're collections, not a database, not to be confused with a database. This might actually turn into the database, but we have data that's collected throughout the processing of the system. We might have start date, end date, if it's an employee HR system. And we can actually put a definition, put them into a dictionary, and say, well, when we want to talk about when the student started at the university, that would be their start date. That would be their graduation date. So it's the name is used in the system, descriptions of entities, relationships, attributes. Everything is included in the dictionary. Some of it ends up becoming part of a database if you want to save the particular data for long-term use. Some of it might actually just go away. It might be temporary data. But once you put all the data together, then you can kind of figure out, oh, this needs to go in a database. This can go in a log file. This could be thrown away. We don't have to store this. And then you can reuse the data, so you don't have duplicate data and inconsistencies between different data, which is how some database designs actually end up being really poor, because they have a student ID, they have a student number, they have a social security number, all these other numbers. And depending upon how you look the student up, you might get a different number of units that they've taken. What's tracked with what. Makes the system run incorrectly, makes the system make mistakes. So this is just an example, brief description normally. What is the date? What is it? How's it used? And maybe combine in a glossary so you can look it up. Because when you start drawing these models, first thing that's going to come to your mind is, what do I call this entity? What do I call this little piece of data that's created? It's a sales receipt. It's an invoice. It's a this, it's a that. And then if you have a common dictionary, you can see how this part of the system is using the sales receipt. And it's not called a printout in this other diagram. Is it the same thing? That causes confusion between diagrams if you don't use consistent words to describe the data or the entities or the processes or something. So, object models. And I've got a few examples. This is just an orientation to the object models. Our next lecture, next week, I'll be talking about more object orientation. The models themselves describe the system in terms of the object classes. I described what an object was already. And it's an object class is the abstraction or the set of object common services, the operations, whatever the object is actually going to be providing. So a lot of new students get confused because they see class diagrams and then they see object diagrams. An object is the same thing as a class. An object is the object-oriented analysis naming convention. The class is the object-oriented design naming convention. And from a programmer's perspective, the class is the implementation of the object. So if you're going to program an object, you're going to create a class, and that represents the same abstraction. So, and that you just have to get used to. Just call them the same thing. But they're actually, object diagrams are actually showing different things than class diagrams, because they're showing a different level of detail. Various different object models that can be produced: inheritance models, interaction models, natural way of reflecting real world, manipulated by the system. In terms of why object models are used, it's closer to reality sometimes. You know, you're representing the world, the real world, in terms of objects. So the big selling point to object orientation is that it's closer to the real world. Yeah, not really, but I don't know. More abstract entities are more difficult to model using this approach, actually, especially if you're not looking at object orientation. It makes no sense to come up with an object model if you're not going to be implementing it with an object-oriented design. It doesn't lend itself well backwards. Class identification is recognized as a different process requiring deeper understanding of the application domain as well. You actually have to know something about object-oriented analysis to do a proper design. Otherwise, you're just throwing darts at a board and seeing where you're going to hit. You know? Structure the system. So object-oriented object models structure the system. Loosely coupled objects, well-defined interfaces between the objects. So a lot of the object diagrams are showing the interfaces. And it's decomposition, concerned with identifying the objects and showing the object interactions. And when implemented, the objects are created using classes. And you have some control over how you're going to coordinate the objects and the operations. So, which is why a class diagram differs from an object diagram, because you're showing the operations, the behaviors, the states of those objects. In a class diagram, you're not really showing that in an object diagram. Here's an example, and this should actually be called an object class diagram, because it's a combination of both. Because normally, if this were really an object diagram, you wouldn't have this stuff in here. You'd only have the name of the object. Looks like a context diagram. Maybe, yeah. All the diagrams look the same after a while. Entity relationship modeling, usually for databases, as we've seen in the database class. Tools for displaying, manipulating entity diagrams themselves. Tools for manipulating the database and the storage. And here are the common symbols. Let's take a look at an example entity relationship diagram. This is an ugly one, actually. We'll be learning you will create an entity relationship diagram in terms of the system model. I don't spend as much time in this class because a lot of these students have taken the database class before, and this isn't the database class. But I'll cover the basic modeling techniques in the weeks to come. So. I believe this is our conclusion. The importance of modeling. Every time you see the importance, I always think, oh, to wrap things up with the importance of modeling. It simplifies reality. Yeah, I say that picture says 1,000 words, I guess. So. Software engineers like models because it put an entire book into one picture, maybe. I build models so that you can better understand the system. So all the thing you're doing in analysis is you're building models. That's your analysis. You're not going out and sitting in the sun and holding your hands apart, wishing for software secrets to come at you. That's not really part of the analysis or thinking, rethinking about everything you did, went wrong with the last project you did. That's not really part of analysis. Analysis is just building models. And through the use of the building models as an exercise, you're learning about the system. It's actually kind of like how you do 20 math problems to learn how to do a problem, how to solve a particular type of problem. That's how you build 20 models, and you understand what the system's going to do. And there's your analysis. And then after you have all the models, you put them together, and here's your design. So analysis and design is quick, which is why they always put them together. Analysis and design. systems analysis and design because they're separate activities, but they're really one and the same because one leads to the other. You spend a lot of time in analysis, very little time in design, a few minutes. So we could build models because we cannot comprehend the entire system in its entirety, so it breaks it down, makes it easier. Models can be formal or informal. We're building formal models. So the more complex the project, the more valuable the formal models become because it allows you to understand the system. There's more. The choice of models to create influences how the problem is attacked and how the solution is shaped. Obviously, if you're only building object-oriented models, you're going to only build an object-oriented solution. You're not considering anything else. Every model can be expressed at different levels of precision. As we've seen, some of the context models were pretty high level. They were showing, sometimes you'll see the internet, and you'll see the system, and it's just two items on a piece of paper with a line drawn between them. You know, that's really abstract. That's really high level. So the amount of detail depends on how easily you can comprehend the model. You actually see what's going on. The best models are connected to reality, showing, actually not on the slide here, and the best models are actually showing something significant about the system. They're not just showing the internet connected to the application. That wouldn't be significant enough to merit a model, I would think. Unless the internet was just invented yesterday. It's kind of like how the cloud pictures are out now. Here's the cloud, here's the internet. To show you that the internet and the cloud are together in the same space. Now, 10 years from now, we're not going to see that. It's too simple. It's not significant enough anymore. But now that we don't understand right now where the cloud is, we can kind of see it a little clearer. No single model is sufficient. Every non-trivial system is best approached through a small set of nearly independent models, hopefully. So we'll see. That is all I have for you in terms of system models as an orientation. Next week, we will actually start looking at how to build models. And I'm going to show you entity relationship, I'm going to show you data flow, and I'm going to show you contextual models, architectural models, which is what you're going to use in your project. So hopefully at this point you have decided on a team, maybe. If you haven't, I've seen a lot of people just showed up, probably for the first time. You can decide upon team members if you'd like. So yes, there's a team project that you have to do. If you don't like working in a team, you can work by yourself. You can have just one person, it could be a team. I would prefer the teams be 4 to 5 students at the maximum. 3 is almost good. 3 to 4 is optimal. 5, it might be too much, but I will allow it. There's a spot on the EMS that I believe is available, should be available. If not, it will be available before next week. That will allow you to put a little description of what it is you're going to build along with your team members. It's just as a checkpoint for yourself. It doesn't really mean anything. It's not a graded assignment. The first graded assignment is the requirement specification. If you're following along with the course and the way things are running, at this point you should have your team, or should have decided how you're going to work. You should be thinking about your project topic and should be starting on the requirements. In the next couple weeks you should finish the requirements. And then you should be on the analysis. And I'm going to wait for about a week, maybe next week, maybe the following week. I'll show you the analysis document template. If you've missed anything, because I know when I said, there's some people who just showed up and you guys raised your hand, oh yeah, that's me. You can watch the videos of the previous sessions you've missed, and that will explain a lot. And also download and look at the syllabus. That will also help you. Any other questions for today that are related to people who have been here or understand what's going on? No? Okay, we're done for today. Have a good one. See you next time. Thank you.